All right, so everybody remembers that I'm going to be gone the next 2 weeks, and you have a substitute lined up. His name is Dr. Wu, and he is going to basically go forward at a pace of about 2 sections per evening. I won't ask him to give you any quizzes or anything, but I'll grade these exams tomorrow and ask him to pass them back on Tuesday and answer any questions that you have. Okay. But then you could expect an exam on chapter 14 shortly after I get back, okay? I'll still have a virtual presence, okay? As long as I'm connected to the internet, I'm still able to assign you your homework in my math lab and everything. Questions?
You said over chapter 14?
13.
Okay.
13. Yeah. I mean, have you noticed that on the homework, when you're doing, these chapter 13 homework problems, but you see it's from chapter 14 in the book I'm using in my math lab. And it's because there's a snafu with my math lab right now, in that they have a different version of this textbook. Essentially the same material, but with a slightly different ordering of the chapters. Whereas this material in chapter 13 for this textbook is chapter 14 in the textbook that they happen to be using. But they offered to fix it, and I told them don't bother because we're in the middle of a semester. And it'll just mess everything up. So in case you're wondering, hey, I'm doing problems from section 13.3, but why does it say in my math lab it's actually 14.3 problems? No, it's because of what I just explained. Okay, so. All right. Now, we're going to continue talking about our multivariable functions, and the discussion that we're going to have this evening is the same sort of discussion that we would have with single variable functions in about the second or third week of Calculus 1 class, and that is limits and continuity of these functions. All right, so what does it mean? So if you understand what it meant back in Calculus 1, then this is just a three-dimensional analog of it. Now let me just actually remind you of what it was back in Calculus 1 involving limits. All right, so we've got the y-axis, we've got the x-axis, we've got the graph of some function f, and we've got some value of x, call it x sub 0. And of course, we've got this point on the graph, and maybe function f is defined there, and maybe it's not. Suppose that the corresponding y value is y sub 0. And suppose that I say that the limit as x approaches x sub 0 of the function f is equal to y sub 0. What does that mean? Now, you ever have to deal with the epsilons and delta discussion back from Calculus 1? Maybe your instructor went through the formal definition using the epsilon deltas and went through some epsilon delta proofs and everything. Maybe not. Depends on what flavor of calculus instruction that he or she subscribes to. There's the reformed method where they don't even bother with epsilons and deltas and stuff. But I'll talk about it a little bit because I know that some of you didn't deal with epsilons and deltas, and some of you did probably. Huh? Who doesn't even know what I'm talking about when I say epsilons and deltas? Okay, all right, so that means that you probably went through the reformed method. Everybody else got the real version. That's okay, nothing wrong. It's just that the epsilons and deltas tend to be a little bit confusing, huh? Right? Okay, so let me just at least give a real brief explanation as to what's going on. Now, in order for this limit to exist, doesn't mean that the function has to actually exist there, but it means that the function cannot have any sudden big changes in value at x sub 0. Meaning that we can't have any like jumps. We can't have any like, jumps in value, for example. Okay. Otherwise, hey, we would approach x naught from the right and have this limit, and we would approach x naught from the left, and we would have this limit. We'd have two different limits. The limit wouldn't exist at x sub 0. Maybe a left-hand limit, maybe a right-hand limit, but the limit doesn't exist. So how do we formalize in mathematical language that there aren't any jumps at x equal x sub 0? So here's like an ambiguous sort of thing. It maybe f exists there, maybe it doesn't. Okay. So anyway, so what we really mean to say when we say that there aren't any jumps, any sudden changes in value of f at x sub 0, is we say that okay, so suppose that we place some small interval centered at y sub 0 on the y-axis, like maybe this little interval right here. And what you need to tell me what the radius of this is, meaning the distance between y sub 0 and either the top end or the bottom end, or whatever. And then what I could do is I can go in and calculate some range of values, except we would want to make this interval really small, like this thing. Some range of values for x, so that I can get a really small interval on the x-axis centered at x sub 0, so that for every x within this little interval centered at x sub 0, that if I take the functional value of those x's in this little interval, that every one of those functional values will be mapped to within that interval on the y-axis. And then I can keep on shrinking this interval on the y-axis, and no matter how small I make this interval on the y-axis, centered at y sub 0, no matter how small that interval is, I can make this interval centered at x sub 0 small enough so that everything in that little interval on the x-axis gets mapped to that little interval on the y-axis. Where this radius on the y-axis, that's the epsilon. And this little interval has the radius of delta. So you tell me an epsilon, and I'll tell you a delta. For every epsilon, there's a delta that works, okay? So that means that if there was some jump, no matter how small it is, could be a jump of a millionth of a unit, we would eventually find it. But what we're saying, though, is that for all epsilon, no matter if epsilon is 1 quintillionth or whatever, I could still find a value for delta down here that will still map everything within that little delta neighborhood about x sub 0 within that ultra teensy little interval about y sub 0. Okay? So everybody kind of understands conceptually? Well, that's okay for our function of a single variable, but how does it work when we have a function of two variables. Well, remember that the domain of our two variable function is going to be a two-dimensional patch of real estate on the xy plane instead of some interval on the x-axis. So instead of having a little interval on the x-axis that we're thinking about, what we're thinking about now is this little patch of domain centered at p sub 0. The p sub 0 here is playing the role of the x sub 0 here. And what we're doing is we're taking the limit as some point p with coordinates x comma y approaches p sub 0 with coordinates a comma b, implying that this is a fixed point, that p sub 0 is a fixed point, and that p is a variable point that we can keep on moving closer and closer, or as far as away or whatever, but in this case we're getting closer. And we have what we call a neighborhood, which is a disk of radius delta, which is the same as this little interval here with our one variable analog here, this interval down here with the radius of delta. So same thing here. And remember that the range of our two variable function is still just the real line. So we're still saying is that we can find for all values of epsilon for z that we can find an appropriate value for delta such that every point p within that delta neighborhood will get mapped on the z-axis within that epsilon neighborhood. So here's kind of another picture, kind of a crazy picture. Here's our epsilon neighborhood up here on the z-axis, and we're saying that the limit for this function is whatever capital L is. So we have our epsilon neighborhood here, meaning that the neighborhood that this interval that goes from L minus epsilon to L plus epsilon. And we're saying that we can find a value for delta such that every point P within that delta neighborhood centered at P sub 0 will get mapped to within that epsilon neighborhood. Same concept in higher dimension. Okay, so here's the official definition of what it means for a limit to exist. Here we are taking the limit as x comma y approaches fixed point a comma b as in p naught of your two variable function f of x y. To say that this limit exists and is equal to L, what does that mean? That means that for all epsilon greater than 0, that there exists a delta such that your functional value, f of xy, this xy, f of xy minus L, so the distance between f of xy and the actual limit, that difference is less than epsilon whenever you are within the epsilon neighborhood of the domain. That's really what this says right here. Remember what this square root symbol says? That's the distance, right? The distance between your x comma y and your a comma b point. A comma b is that fixed point that you're letting x comma y approach. So this is the distance between x comma y and a comma b. So that distance is less than delta. So for every epsilon we can find a delta. Even if epsilon is extremely, extremely small, we can still find a small enough delta that works. For all epsilon, we can find a delta. And not only that, here's a new wrinkle in it, is that P, remember P is that variable point, will approach P naught with coordinates A, comma, B from all different paths. And this is what makes it a little bit more exciting for the two variable function compared to the one variable function, because one variable function, you're either going to approach x naught from the right or from the left. But here in two dimensions on the domain, you could approach the fixed point from an infinitude of paths. You can go from the bottom to from the top, from the side, from some swirl or whatever. That is interesting. And here's the thing. If we're going to say that the limit exists at P naught, it has to be the same limit along all paths. Remember, from Calc 1, we could have a right-hand limit and a left-hand limit. And if those two limits didn't map, then the limit at that point x naught wouldn't exist. Well, same thing here. If you take the limit along one path as x comma y approached P naught, and you got some limit, and then you calculate the same limit but along a different path, and you got a different limit, well, guess what? The limit doesn't exist at that point. So it's kind of interesting. So we'll do at least one example where I'll show you how a limit does exist, because we'll come along some different paths. All right. Let me open up my textbook here real quick. So, the same sort of values or limits that you would expect from single variable functions, those same limits apply for the two variable or multivariable in general sort of functions exist. So the limit of a constant function is a constant function. The limit of a linear function like f of xy is equal to x, or f of xy equals y, or f of xy is equal to cx plus dy, or whatever. Those are just, you plug in the appropriate value for a, or for x or y or whatever. Just plug the numbers in. Just evaluate them, right? So, and so that goes for all your familiar functions, your polynomials, your absolute values, your sine functions, cosine functions, rational functions, logarithms, as long as the function itself is defined for the input that you put into it, then you're good. Also, the limit of the sum of two functions is the sum of the limits. Same thing for differences, constant multiple. So the limit of the constant multiple is the constant multiple of the limit. Products, quotients, as long as you're not dividing by zero. Powers, ratios, as long as you're not dividing by zero. Right? No surprises there. We could prove all these if we chose to, using epsilons, deltas. I'll leave that for you, especially for the math majors in the room. Let's do an example here. Number one. Suppose that we're going to, let me get my pen out, calculate the limit as x comma y approaches 2 comma 8. Of 3x squared y plus the square root of xy. Okay, so again, The 3x squared times y, that's a polynomial term. Just plug the numbers in. The square root function is good as long as you're not taking the square root of a negative number. Okay? So, and of course, with x being 2 and y being 8, that we're letting x and y approach, we're good. We're not taking the square root of a negative number. So plug in the numbers. 3 times 2 squared times y, which is 8, plus the square root of xy, which is 2 times 8. So we're talking about what 12 times 8 is 96, plus the square root of 16, which is 4, so that's equal to 100. Okay? No surprises? We need to talk about what it means for a set to be open and closed. And for the math majors in the room, very important concept here as well. But we'll also need to know, all of us need to know about when we start talking about surface integrals and line integrals and stuff in the last chapter of the book. So suppose that we've got some region R on the plane. That's what the R2 is there. That's XY plane. Now, an interior point, call it P, of the region R. So what does it mean for that point to be an interior point? Well, it lies entirely within the region. And that means that it is entirely possible to find a disk. You can find a disk. Not all disks will be within the region, but you can at least find some disk centered at that point. That is entirely within the region. That meaning that it contains only points of R. And I'll show you a picture here in a minute. Also, we could have a boundary point that lies on the edge, and that every time that you put a disk centered at that boundary point, part of the disk will lie off of the region and part of it will lie on, no matter how small the disk is. That's what it means for a point to be a boundary point. So here's a picture to illustrate what we were talking about. So we got some region R on the plane. That's the pink blob. And here's point P, and it's our interior point. We can find at least some bound or some disk centered at P that lies entirely within R. And no matter how close that you get to the boundary, as long as you're not on the boundary but within R, you can still find some disk, a disk with a small enough radius that will be entirely within R. And Q is a boundary point because of the fact that every disk, no matter how small, that we place centered at Q, part of it will be contain some of R, and part of it will contain or be outside of R. Okay, we need to understand to have those concepts down and those definitions down in order for us to now talk about what it means to have a set that is open and what it means for a set to be closed. Not all sets are open, not all sets are closed. In fact, many sets are neither open nor closed. But you won't have any sets that are both open and closed. Now, a region is open if it consists entirely of interior points. Let me illustrate that with an example here. It's a real easy example. All right, on the real number line. All right, here's the origin 0, and here's 1. How many numbers, how many real numbers are there between 0 and 1? Infinitely many. How many rational numbers are there between 0 and 1? Infinitely many. How many irrationals are there? Infinitely many. That's true. You have a whole universe of numbers. Uncountably many. There's more numbers between 0 and 1. In fact, there's more numbers on any interval, no matter how small the interval. There's more numbers on any finite interval on the real number line than there are stars in the universe, or grains of sand on all the world's beaches combined. Amazing. Now, an example of an open set is the set of real numbers on the interval from 0 to 1. So let me ask you, what is the largest number on the interval from 0 to 1? 1's not in that set. What's the largest number? That's greater than 0 but less than 1. It's a trick question because the answer is there's none. And then also, what's the smallest number in that set? What's the smallest number greater than 0? Yeah, again, it's a trick question, right? Because there isn't any. So there is no boundary to this set, is there? But for every number that's in this set, even if it's 0.999999 with a million nines in that decimal, I can always find a point that's halfway between that number and 1 and declare that distance as the radius of my little interval. Okay? So every number within this set, within this interval from 0 to 1, is an interior point. I could think about an extremely small number, 0.000, million zeros, 1. And yet I can find some other real number that's smaller than that number, but greater than 0. And then take the difference between my number and that other number, and then that would be the radius of my little interval. And we can repeat the process. Okay? So that's an example of an open set. Okay? That's an open set. No boundary points there. Okay, an example of a closed set would be if I were just to include 0 and 1 as the endpoints now. And of course, in this case, we just simply have 0 and 1 as the two boundaries. And it includes those two boundaries. The set includes those two boundaries. 0 is a boundary because every interval that I center at 0 will include at least one negative number and one positive number. And 1 is also a boundary point because every interval that I center at 1 will contain a number less than 1 and a number greater than 1. Okay. Does everybody understand the difference between an open point and a closed point? Or an open set and a closed set? Interior point versus a boundary point? Any questions about that? Kind of obscure sort of stuff to start thinking about. And here we're still thinking about if we are going to be taking the limit of a function at a point on the domain that happens to be at the boundary of the domain, we still need to consider all paths that lead to that point, all paths within the domain. Okay. All right, so how to compute limits? Well, we know the obvious ways of computing limits with our nice and easy functions, right? Polynomials, square roots, logarithms, trigonometric functions, etc. But what about this function? They talk about on page 910. What about f of xy is equal to x squared minus y squared over x minus y? Is this defined everywhere? No, it's not defined along, wherever the denominator is equal to 0. So we would have to exclude the points in the domain along the line x equals y, or y equals x. So if you can imagine the xy plane, every value, every point, I should say, on the plane is good, except on the line y equals x. That nice diagonal line that goes up. Because this function's not even defined on. Now, suppose that we wanted to compute the limit as x comma y approaches 4 comma 4 of this function. And your first reaction might be like, you must be kidding, because 4 comma 4, that's x equals y. This function is not even defined there. But if we remember from Calc 1, does the function need to be defined where we take the limit? The limit could exist there, even if the function's not defined there, right? So that's the same thing here. This function's not defined at 4 comma 4 because at that point the denominator is equal to 0. But of course you could factor the numerator and of course we'll have x minus y times x plus y divided by x minus y. Cancel the x minus y's as long as, because we're told that x is not equal to y. And we are going to approach 4 comma 4 along some path that does not cross the line y equals x. It's like I'm going to go from this point in the field to that point in the field. And as long as I don't cross that stream, that happens to be the line y equals x, I'm good. Now, of course, 4 comma 4 lies on that line, but we're not going to cross that creek. We're not going to cross that line. But now look what we have here. After you cancel the x minus y's, now we have the limit as x comma y approaches 4 comma 4, and now we have x plus y. What is the relationship between the function x plus y and the function x squared minus y squared over x minus y? What's the relationship between those two functions? Are they the same function? They are exactly the same functions except what? Except for their behavior along the line x minus y, or x equals y. This function x plus y is defined along the line x plus y. In fact, it's defined everywhere. X squared minus y squared over x minus y has exactly the same functional values as x plus y. The only difference between the two functions is that the original function just happens to not be defined along the line x minus y. So if you were to take a look at the surface graph of the two functions, the two surfaces would look exactly the same, huh? Except just like for the the one variable function, there might be a hole where a function is not defined at a particular point. Well, instead of a hole on the surface, you would just see kind of like an imaginary sort of line sort of taken out of the surface, huh? Like someone took an ultra thin sort of laser and removed a slice out of the surface, huh? That's kind of what you might imagine the surface graph would be for the original function. That slice line right above the line x equals y, huh? So the original function doesn't exist at 4 comma 4, but the limit is still going to be 4 plus 4 equals 8. Okay, so everybody understand the distinction? The function does not exist at 4 comma 4, but its limit is 8. Okay, any questions on how this went down? So, you might have to compute the limit of a function, kind of like what we did here. And if you try to plug the numbers that for the coordinates of the point that you're approaching and the function is not defined there, then see what you can do to algebraically come up with an equivalent function that is defined there. And then plug the numbers in. And the functional value for that equivalent function will be the limit for that original function. Everybody understand what I'm getting at here? Okay. So here's kind of a picture of what we were just talking about here. It kind of looks like a plane, huh? This is the surface graph of x squared minus y squared over x minus y. It's really the same as the graph of x plus y. But notice that little slice that's taken out of it. This is the part of the graph that lies along or above the line x plus or x equals y. I mean, okay. All right, let's do another example here. So this time we're going to take the limit x comma y approaches 4 comma 1 of the function xy minus 4y squared over square root of x minus 2 times the square root of y. So what happens if you plug 4 in for x and 1 in for y? You're dividing by 0, huh? So what do we do? Well, let's see if we can find a function that is algebraically equivalent to this one everywhere except for where this one's implied. Okay? So, hey, guess what? Maybe we can factor that numerator. Maybe pull out a y, or better yet, maybe we can multiply the numerator and denominator by the conjugate of the denominator, meaning multiply top and bottom by square root of x plus 2 times the square root of y. This is another way that we could do this. Okay, maybe that'll work. So what happens if we do it this way? Now, let's take another pass through here. Limit x comma y approaches 4 comma 1. Now, in the numerator up here, I'm going to factor out a y. So I have y times x minus 4y times the square root of x plus 2 times the square root of y divided by, and in the denominator I have x minus 4y, huh? Difference of squares, right? You take a binomial times its conjugate, you get a difference of squares. We learned that from algebra class. Then you can cancel the x minus 4y's, leaving us with the algebraically equivalent function of y times the square root of x plus 2 square root of y. So y times the square root of x plus 2 times y square root of y. And now we can go ahead and plug in 4 for x and 1 for y. So you have 1 times square root of 4 plus 2 times 1 times the square root of 1. And that's 4, huh? Everybody see how that goes? Any questions so far? Pretty straightforward. So as long as we did not approach 4 comma 1 along the line x equals 4y, what was so special about x equals 4y? Because when x is equal to 4y, let me go back. Oops. When x is equal to 4y, then you have square root of x minus 2 square root of y being equal to 0, huh? Why is that? Well, take square root of x minus 2 times the square root of y, set that equal to 0. That means square root of x is equal to 2 square root of y. That means x is equal to 4y. Aha, that's why. So we could take this limit as long as we stay off the line x equals 4y on the domain. And then write that equivalent algebraic function and then plug in 4 for x and 1 for y. And we've got our limit. And what do these arrows mean? That means that we are approaching 4 comma 1 along some path that does not cross that line of death. Right? Okay. All right, let's do another example. Number 3. Here we're going to see where a limit doesn't exist. Ooh, spooky stuff, right? So let's go ahead and take the limit as x comma y approaches 0 comma 0 of the function x plus y squared over x squared plus y squared. Now, as you can see, number 1, you can't just plug in 0 comma 0 because you'll be dividing by 0 and that's no good. But also you cannot really manipulate that algebraic function in a way that you'll get an equivalent function that will cooperate, huh? So, what do? So we would have to investigate different paths. So let's take a limit maybe along the path y equals x. Along the path y equals x. Now along the path y equals x, that means either x equals y or y equals x. And when you do that, you substitute y for x or x for y in the function. So I'm just going to replace y by x in the function. And then that will give us a single variable limit. Everybody see what I'm doing here? So what will this do for us? So we'll have 2x squared over 2x squared. So then we'll have a limit as x approaches 0. 4x squared over 2x squared. Cancel the x squareds, giving us 2, right? Oh, okay. So 2 is the limit, right? But this limit would have to be the same along all paths, huh? So maybe we should try another path to see if we get the same limit, huh? Okay, well, let's try along a different line. So how about along the line y equals 2x? In which case, when we take our limit, we'll replace y by 2x now. From this original function, replace y by 2x. So we'll have x plus 2x squared over x squared plus 2x squared. Okay, and then numerator we got 3x squared over x squared plus 4x squared, which is 5x squared. Oh, okay, this is looking interesting here because of the fact that now we have 9 times x squared over 5 times x squared. X squares cancel, leaving you with 9/5, huh? Oh my God, well this gives us a different limit, huh? We still approach 0, we still approach the origin, didn't we? But along 2 different lines. So when you are not sure about this limit that you're trying to take and you've approached along one path, well, try along a different path. Maybe, if you approach along the line y equals x, then Try it again, y equals 2x or 3x, or in fact, y equals mx. And as you can see in the example in the book, what they did was that they approached along the line y equals mx, where m is some constant value. And it turned out that the limit was 1 plus m squared over 1 plus m squared. So the limit really depends on the slope of the line that you are using as your path, huh? In which case, you're not going to have the same limit for different paths, right? In which case, the limit doesn't exist. In order for the limit to exist at the point 0, 0, the limit would be the same along every path that leads to the origin, huh? So in this case, the limit doesn't exist. So limit does not exist. Any questions on this? So here we just approach the limit from different paths, and we see that we get different limits according to the different paths that we took for the same problem. Moving along here. And here's kind of a picture of the surface graph of this function here. You know, it looks really strange. You can see that you've got this really deformed top there. And you come to the origin along some different paths on the xy plane, that you'll see that take you to some different values. It's really a strange looking surface, huh? All right. So here you see the procedure that will tell you exactly the same thing that we just talked about. This procedure that says if the function f of xy approaches two different values as x comma y approaches your point a comma b along two different paths in the domain of f, then the limit does not exist. Okay? So now we know how to calculate the limit and how to show that a limit doesn't exist by showing it doesn't exist along, or that you have two different limits along two different paths. All right, so now let's talk about continuity. The ideal of continuity is extremely important when discussing functions. What does it mean for a function to be continuous at a point? Well, the function is continuous at a point, provided that the function is defined at the point, and that the limit as x comma y approaches that point exists, and that the limit is equal to the functional value at the point. Same definition as for the one variable function. You'll have a question like this on the homework too. What three conditions must exist in order for a function to be continuous at a point? There they are. So, look, the first two conditions could exist and still it's not continuous. For example, if we have this one variable function and we have this hole right here at x equals x naught, and the limit is L1, but f of x naught is really L2. Okay, so f is defined at x naught, and its value is L2, right? But its limit is L1. This is not a continuous function. At least it's not continuous at x is 0. In order for it to be continuous, we need to fill the hole so that the limit as x approaches x naught is really equal to f of x naught, which is L1 in this case. There's the two variable analog. So let's take a look at example 4 here. So we're going to take a look at this piecewise defined function. F of x comma y is equal to, and we have this curly brace. First of all, we have 3xy squared over x squared plus y to the fourth. And that's going to be if x comma y is not at the origin. And we're saying that f is 0 if x is at the origin. Okay. Well, it could be that this function right here is not defined when x and y are both 0, but maybe the limit does exist and is equal to 0 when x and y approach 0 along any path. So, look, we have three things to check to see whether or not this function is continuous at the origin. Otherwise, this function is continuous everywhere. The only place that we have to check is at 0, 0 at the origin. So, number 1, is the function defined as 0, 0? Yes, it's defined to be 0. And then we have to check the limit. Well, if you were to gander over to the top of the next page, you could see that if you were to take the limit as x comma y approaches 0, 0 along the path, let's use the path. In this case, you have the parabola x is equal to my squared. You could probably dream up some other path that might give the same results. But along the parabola x equals my squared, where m is some constant, well, replace x by my squared in the function, and you have 3 times my squared times y squared over x squared plus my squared raised to the 4th power. Why am I doing that? I don't know. Let me back. You guys weren't making any noise. You need to tell me if I'm screwing up here. No, this is actually my squared squared plus, where's Astrid? You need to pay attention. She's my eagle eye. So let's simplify this. Now in the numerator we've got 3 times m times y to the 4th, huh? And then we have m squared times y to the 4th plus y to the 4th. So you can cancel the y to the 4th between numerator and denominator, leaving you just with, and then of course that's a constant, so that leaves you with 3m over m squared plus 1, I guess, which of course has a value that depends on m. Change the parabola, we change the limit. So does the limit exist at the origin? No, it doesn't. So it violates the second condition for continuity. So is this function continuous at 0, 0? No. It's probably continuous everywhere else, right? But certainly not at the origin because the limit doesn't exist there, huh? All right. So this function f is not continuous at 0, 0. Okay. Moving on here. So here this shows a picture of what we were looking at here for this function that we were taking the limit as x approached 0, 0 along these different parabolas. Of course, here it shows some different values for m. M equals 1. The limit would be 3/2. M equals -1. The limit would be -3/2, etc. All you need to do is show for 2 paths, huh? And that's enough to show that the limit doesn't exist. And this right here shows the graph of this function that we were just playing with. And as a matter of fact, you see at x comma y being at 0, 0 at the origin right here, that some strange behavior is happening at the origin, huh? So, what is the limit of the function at 0, 0? Well, it depends on what path that you take. But it certainly isn't just one value. All right, what does it mean to take the composite of 2 functions? That means that the output of one function is the input for the outer function, huh? So like e to the x squared or the square root of x squared plus 1 and stuff like that, those are composite functions. And just like it was for the single variable functions, you know, your function, in this case the 2 variable function, that is composed with the single variable function, that composite function is going to be continuous as long as both the outer and the inner functions are continuous. Okay? But you got to be careful. It could be that the inner function is continuous everywhere, but the outer function is not continuous at a particular point in the range of the inner function. So, it's at least a little bit more simple for the outer function, because the outer function is going to be a single variable function because of the fact that the inner function will typically be a 2 variable function. Okay? Example number 5. So for part A, we've got the function h of xy to be equal to the natural log of x squared plus y squared plus 4. Where is this function continuous? Well, it's going to be continuous everywhere it's defined, right? Because the natural logarithm, perfectly fine function. It's defined for all positive inputs, right? So take a look at the inside function, this 2 variable function. So the whole composite function is going to be good as long as the interior function, the x squared plus y squared plus 4, is greater than 0. Now we know the log function is not defined at 0 or any negative number, so only for positive inputs, right? So x squared plus y squared must be greater than -4. Well, look, x squared plus y squared is never going to be negative, huh? It's always going to be greater than or equal to 0. So guess what? Any value for x and any value for y. So in other words, the entire real plane is going to be the domain for this composite function. Does that make sense? There aren't any restrictions on x and y, huh? So the domain in this case is just all of R2. and it's continuous. Also continuous on R2 as well. B, here we have h of x comma y equal to e to the xy. Outer function is the exponential. The inner function is x over y. The inner function is going to be not defined when y is equal to 0. Otherwise, hey, guess what? The exponential is defined for all inputs, huh? But the interior function is not defined at when y is equal to 0. So h is continuous when y is not equal to 0. Or if you want to use set builder notation, there. What does this symbol mean, by the way? This little sideways pitchfork. It means it's element of. So x comma y is the element of R2, the plane. In other words, x comma y is a point on the plane, provided that y is not equal to 0. So that's another way of stating the set of numbers for which this function is continuous. Okay. Take a look at our last example. Here we're taking a look at functions of 3 variables. So same discussion for limits, continuity, etc., as we were just doing with 2 variables. Let's do a real quick example here. Actually, there's 2 examples here. For part A, suppose that we've got the limit for this 3 variable function. So we're traveling in 3-dimensional space, letting x, y, z approach the point 2, comma, pi over 2, comma, 0. And the 3 variable function is x squared times the sine of y over z squared plus 4. This function here is a function where you put in a value for x, value for y, value for z, and out pops just a single real number. Huh. Now let's take a look at this function here. It's a rational function, so obviously we cannot divide by 0. But of course, z to the 4th is never going to be 0, huh? Or it's never going to be negative. So z to the 4th plus 4 is never going to be 0. Huh?
It's supposed to be z squared.
Is it z squared?
Yeah,
Okay, thank you.
There, but,
Yeah, so, but yeah, we'll have pretty much the same result anyway, right? Just plug in the numbers. Okay, and then the numerator, you got x squared, perfectly fine polynomial. Sine of y, that accepts all values for y. So, you see any restrictions there? Anything that's going to explode? Plug any numbers in? Anything? No, yeah, so nothing's going to blow up. And indeed, when you plug in 2 for x, so 2 squared is 4, plug in pi over 2 for y. What is the sine of pi over 2? It's 1, right? And then z squared plus 4 is 0 squared plus 4, that's 4. And so the value of that 3 variable function at that point is 1. Hey, like I said, rational functions are continuous everywhere as long as the denominator is not equal to 0, huh? B. Find the points at which this function h of x comma y comma z is equal to the square root of x squared plus y squared plus z squared minus 1, or is that continuous or not continuous? So, look, we're talking about square roots and squares and stuff. So this is all good as long as the square root function is defined, right? And it's going to be defined as long as you're not taking the square root of a negative number, right? So the radicand, x squared plus y squared plus z squared minus 1, you set that to be greater than or equal to 0. That means that x squared plus y squared plus z squared must be greater than or equal to 1. So as long as you are either on the boundary of the unit sphere or outside of it, then this function is going to be defined and continuous. Does that make sense? What do I mean by the unit sphere? Sphere of radius 1, exactly. And isn't that what we have when x squared plus y squared plus z squared equals 1? That's the unit sphere, huh? So, do you see where we say that you're either on the boundary or outside of the unit sphere when we say this? Okay? So, the set of points for which this function is continuous, we could use set builder notation. So use that set element notation. What does R3 mean? Three-dimensional space, huh? So there's the set of points for which this function is continuous. Okay? So that's pretty much it for 13.3. Any questions so far? So Dr. Wu, when he meets with you on Tuesday, is going to talk about derivatives. In particular, partial derivatives, where you basically are going to take a two-variable function and treat one variable as a constant and differentiate with respect to the one variable that you are differentiating with respect to. So if you're going to differentiate with respect to y, then you'll treat x like it's a constant. Okay? So that's it. All right, so you'll have some fun with Dr. Wu. Now, so take a 10-minute break and come back and be ready to take the test. And we will start at 7:35.